Can you see my screen now?
Yes, sir.
Yes,
All
sir.
right. Okay. Thank you. Okay. So in the last lecture, we introduced inner product space, and we first introduce inner product, and then we introduce inner product space. So what is an inner product? Inner product is a map from so if suppose V is a vector space, then a map from V cross V to F. F is the field, is uh, called an inner product if it satisfies four properties like non-negativity and positivity, then the conjugate symmetry, then linearity in the first component of the inner product. If it satisfies these four properties, then we say the given map is actually defines an inner product on the vector space, and a vector space together with an inner product is called an inner product space. So then we saw some simple properties of, of an inner product and also some examples. But then at the end, I gave you like a result or as an exercise that gives you a way to define arbitrary inner products on a given vector space. So for example, so let me recall what was that result. That result says that we have let's say two vector space, let's say V and W on the same uh, field or the same field, and suppose that we know a vector an inner product on W. Okay, this is now. And if we and suppose that we have a linear map from V to W, which is linear. So we have a map from V to W, which is linear and also non-singular. That means null space of T is actually 0. So it's a linear 1-1 map. Okay. So this sometimes this equation, this condition is also known as non-singular. Since when we are in finite dimension, then this non-singularity is equivalent to invertibility. But when we are infinite dimension, then this non-singularity means the space of T is 0. Okay, that's why we sometimes we an invertible matrix we call it as a non-singular matrix, because there this one-oneness and ontoness both are same. But for infinite dimension, we need non-singularity. That means we just need null space of T is the zero space. So if these are the conditions given, then using this we can define a map. Let's say this rho T from V cross V to F. How it is defined? You just take two elements here, U, V, and then assign it to this one, T of U, T of V, inner product over W. So since this inner product is given to us, and then you can check that if we define in this map this way, then this is a function from V cross V to F. It's a well-defined function, and it also satisfies four properties of the inner product, and therefore it defines an inner product on V. So using an inner product on W, you can define an inner product on V. Now there are like infinitely many such maps you can define, and therefore you can say that in fact there are infinitely many. One can define infinitely many inner product on a given vector space. So for example, let me give you one more example here. Say this one. So let me remove this one. It was just to recall what we did in the last class. And now we start today's lecture with an example. So we have let's say we have a vector space over F, which is of finite dimension. Let's n be the dimension of V. Okay. All right. Then can you use that previous exercise or that result? Can you define or can you give some idea to define and some inner product on this vector space V? So just use the fact that V is a vector space of dimension n. can you use that result to define inner product on this? So what you need? You need a W, right? And an inner product on W. So can you first say, okay, if we take W this, then we can easily define a linear invertible map from V to that W. So what should I take here? And you also have an inner product on that W.
B dash.
V
Sir,
itself.
Rn.
Yeah, so one of you said V dash. V dash you can take, of course, V dash, but you need an inner product on V dash because you need W, of course, but you also need W such a way that you know some inner product on this W. So if you can take W as V dash, and you can also, since V and V dash both are of same dimension, there is a, you can also define linear invertible map easily. But then you should know some inner product on this W. If you know that, then of course you can use V dash. So the only thing is that you should know some inner product on this. Okay, so either you tell that, okay, you consider this inner product on V dash, and then you can use this result to define. So I agree, but you need an inner product on this V dash. Then some of you said you can take Rn. Rn you can take, of course, but then you just make sure that the function which you define that satisfy all the properties. So you can take Rn here, but just to make sure that things are not problematic there. For example, so just remove this thing. So you said you take W as Rn, and then what is the inner product on this?
Standard.
You can take a standard inner product, that is also fine. So up to this is fine. Then what would be the linear map? T,
सर डायमेंशन से n है तो आइसोमॉर्फिज्म एग्जिस्ट करेगी.
right, karegi. So will be fine. But then you should remember that this V is a vector space over F. I'm not saying over R. So if it is over C, then this whatever you are trying to define, that may not be a linear map.
Rn की जगह Fn ले लेते हैं.
Right. So if you do this for Fn, because then there is no problem, then you know that there are several ways to define uh, linear invertible map from V to W because they are of same dimension. So one way is that you take you fix a basis here. Let's say so this is fine. This is uh, very clear that we can take W, and we know W. We can also take an inner product, which is the standard inner product. Standard inner product on W. So this is the standard for inner product. And then, for example, to define inner invertible map from V to Fn, there are several ways. One way is that you fix basis for V and W and send basis elements to basis element. For example, this, suppose this is a basis of V, and let's say you have a standard basis for Fn. Okay, then you can define this T, which is from V to Fn. And how you define? You just send this Vi to Ei for all I equal to 1 to n. So what is this map? This is actually, if you take any vector, this would be of this form, right? And then it goes to this alpha I Ei. But you know what is this alpha Ei? It is just this vector alpha 1, alpha 2, and so on, right? Because E1, E2, En, you know. So if you assume that these Eis are in the form of a column vector, then you can write it in this. So this is your linear map. Clearly, this is a linear invertible map. So you can use that previous result. That means this map rho t from V cross V to F How it is defined? You just take any two vector u and v and then send them to uh, sorry send them to this one, the standard inner product of t of u and t of v. So what is this? So if you just write, let's say, uh, if you write u as alpha I vi and v as, let's say, beta I vi, I equal to 1 to n, I equal to 1 to n. Suppose they are the vectors which are written in this form. Then what it would be? Can you tell me what it would be in the right hand side?
alpha I beta I bar.
Yeah, alpha I beta I bar, but summation
Yes, sir. Summation.
I equal to 1 to n. Now you see that this is, you don't have to prove that this is a linear map. What you need to check is that whatever you have used here, that satisfy all the hypothesis of the result. Once you agree that okay, this is fine, then the map which you are defining using that result is an inner product. So you don't have to check that this is an inner product. You just say that this defines an inner product because of that result. Okay. Now you can see here this map clearly you are defining using the basis of v and fn. But you know there are infinitely many bases. So if you change the basis for v or fn, then you can still define these isomorphisms the same way, but you will get a different like the different alpha I beta I for every uv, and you will get a different map. So what I'm saying is that if you change the basis, you will get a different map and therefore a different inner product. So there are, this way, at least you can say for finite dimension vector space, using this example, we can say that there are infinitely many ways to define an inner product on a vector space. But the same idea will work for infinite dimension also. And the same way, because that result is also valid for infinite dimension, and therefore using similar way, you can define an inner product on any vector space. So there are infinitely many inner products one can define on a given vector space. All right. So let's move on. I hope this result is clear. So actually, I have given, if you look at the problem sheet, I have given an exercise that says that to define different inner products on Rn or R3. I think I fixed some vector space there. So that was just to check whether you have understood this result or not. All right. So let me introduce the next term. This is orthogonal orthonormal set. Okay. Do you know, I mean, what is orthogonal orthonormal set? Because some of you have learned this inner product.
Yes, sir.
Yeah,
Yes,
what
sir.
it is?
इनर प्रोडक्ट जीरो हो जाए तो ऑर्थोगोनल, और उसका नॉर्म वन होगा तो ऑर्थो नॉर्मल हो जाएगा विथ ऑर्थोगोनल कंडीशन.
Okay. Okay. Yeah, so he's saying that if the inner product of two vectors is zero, then they are called orthogonal. And if a vector is of length one, then it is called an orthonormal. So if you, instead of saying a vector, if you have a, can you please mute? Yeah. So if you, instead of a vector, if you suppose you have a set of vectors in an inner product space, you should be in an inner product space. So for orthonormality or orthogonality, you should have an inner product. So with respect to which you can talk about orthogonality. So if you have a set of vectors and every distinct pair of vectors is orthogonal, that means their inner product is zero, then this set is called orthogonal. And if every vector in this set is of length one, that means inner product of every vector with itself is equal to one, then it is called an orthonormal. So let me define it here. Suppose that we have a, so as I mentioned that we will consider only R and C, that means field as R and C. And suppose that we have a vector space V not vector space, we need inner product space. So inner product means it is a vector space together with an inner product. So when I say inner product, so you assume that there is an inner product, and I'm talking about, and whatever I'm saying for this inner product, which is defined on this V. So V is an inner product space over F. Okay. Then let me define the orthogonal set. So let S be a subset of V, and U and V are two vectors. So then these vectors U and V, they are said to be orthogonal if their inner product is 0. Now you know that because of the symmetry, inner product of UV is same as inner product of VU bar. So that means the complex conjugate is also 0. If the complex conjugate of a number is of a complex number is 0, that means the number itself is 0. So that means this inner product of U is 0 if and only if inner product of V and U is 0. So that means we just replace U and V or interchange with U and V here. So and therefore you say that when U is orthogonal to V, then V is also orthogonal to U. So that way. So in particular we say that they are orthogonal. This is for two vectors. And similarly, we say that this set S is called an orthogonal set. Orthogonal set if for all distinct pairs, let's say U and V, not U and V, let's say V1, V2, any distinct pairs V1, V2, in V, we have like inner product of V1, V2 is 0. So that means every distinct pair of vectors are orthogonal to each other, or every distinct pair of vectors is orthogonal to each other. So this is for orthogonal. The set S is called orthonormal.
Sir, V1, V2 belong to S, na?
V1, V2 belong to, yes, S,
S.
not V. You're right. S. We are talking about S. Yes, thank you. So S is called orthonormal if it satisfies two things, that it has to be orthogonal first. So S is orthogonal. And second is that length of every vector, which we are using by this notation, length of every vector V in the set is equal to 1. Then we say that this set S is orthonormal. All right. And when we may also, or in some books you can also see, or you may see that they use this notation. So if U, V are orthogonal, two vectors are orthogonal, then sometimes we also write like U is perpendicular to. Okay, so this means the same thing, that the inner product is 0. So for example, so this is the terminology we'll use. For example, let me give you some examples here. So suppose that, so let us consider the inner product space we have considered so far. So for example, if you look at this Fn, whether it is Rn or Cn, with respect to the standard inner product. Okay. Now, so with standard inner product, right? It's standard inner product on Fn. So this is the inner product space. Now, can you give me an example of vectors which are orthonormal here, or let's say orthogonal first?
Basis.
Sir, standard
Which-
basis.
Standard basis. So standard vectors are orthogonal to each other, and not only orthogonal, you can verify that they are orthonormal. So here, example of an orthonormal set is E1 to Ek, where k is less than equal to n, is orthonormal. So this is one example, but if you like just consider take any set and then you just check whether the inner product is 0 or not. Then if it is 0, then you say that if it satisfies the definition of orthogonality, then you say that it is orthogonal, otherwise it is not. For these vectors, it is easy to check that they are orthonormal. Similarly, you can take let's say let us consider this V as n cross n matrices over F. And what is the inner product here? This is the standard inner product. So let me recall what was the inner product here. So if you take any two matrices A and B, then their inner product is defined by the trace of A, B star. Star is the complex conjugate transpose of B. Okay. Now this is the inner product. This is the inner product space. And on this inner product space, if you look at this set, which is containing the elements of the form of this form. So what is this EP sub E superscript P comma Q? So this is just a notation. So this is a matrix which has one. This is a matrix of size n cross n, which has one on pth row and qth column. So that basically it at pq position it has one, and rest of the entries are 0. So for example, what does it mean? For example, if let's say n is 3, then E23 is actually a matrix which has 0 everywhere except at 2, 3 positions. So that means this one. So this is an example when n is 3. So if V is n cross n matrices, and if we consider this kind of matrices, then this set S, which is let's say collection of all matrices of the form this, where P and Q belong to 1 to n, then this set one can check that this is an orthonormal set with respect to this product, this inner product, the standard inner product defined on this set. So this you just verify, okay? So it was simple verification. So you sorry. So you verify this, okay? Similarly, let me give you one more example. So these verifications you can do, just you have to check the inner product. You take the inner product of two element, any two element, and check whether they are their inner product is 0 or not. Once their inner product is 0, then you say that it is orthogonal, and then for every vector, take any random vector from this set and check what is the norm of the, or sorry, the length of this vector. If it is 1, then you say that this set is also orthonormal. Similarly, if you take this vector space, a set of all continuous function defined on the closed interval 0, 1 to f. F is either R or C, together with an inner product. So you consider with this V with the standard for inner product on this. That means defined by this inner this integral here 0 to 1 ft gt1 dt. Okay, and then this is an inner product space we have already verified. On this vector space or on this inner product, if you consider these functions, so f and t is root 2 times cos 2 pi n t, and similarly if you define g and t,
सर
which is yeah.
सर मैट्रिक्स में जब हम लेंथ फाइंड करेंगे we have to find the determinant.
No, length is what? Length we have
Sir,
defined now. If you look at our definition of the length and angle, if you go back to your previous lecture notes, then we have said that the length means this one. So if V is an inner product space, then for any vector V in V, the length is defined by this. It is the square root of inner product of V with itself. This is what we are saying. So this is the length.
Yes, sir. But if we take two metrics,
Yeah, just a minute. Just
3 by
yeah, just a
yes.
minute. Yeah, just a minute. So here now this is true for any vector, any inner product space. In particular here for this example, this V is n cross n, the set of n cross n matrices. Okay, so now you replace this V by let's say n cross n matrices over R. Now you take V any element, so element of this vector, this vector space, which is the space of matrices, are matrices. So you take any V, that means you take any matrix. So V is any matrix. So element of this vector space are matrices. So you take any vector in V, vector means any element. So elements of a vector space are called vectors. So it doesn't have to be of the form of, let's say, some ordered pair or some ordered tuple. So it is an element of a vector space is called a vector. Okay. So if you take any V in V, so in this case you take any V means any matrix, let's say A in V. If you take any matrix in V, then the length of A means you look at this and how it is defined. It is defined by this. Now
Yes,
this is
very
the
clear. Trace. Yes, sir.
yeah. So it is the square root of trace of A star. So this is the length. Okay. So there is no
Yes, sir.
involvement of determinant. Okay. All right. So I was talking about this example here. So for this inner product space, if you look at these functions f and t and g and t for n, where n is n belongs to natural number, then this set, if you look at this set f1, f, f1, g1, f2, g2, and so on, then this is an infinite set. And not only an infinite set, it is an infinite orthonormal set. This is an infinite orthonormal set in V. So we have also given you, or I have given you one example of an infinite orthonormal set in an infinite dimension inner product space. This again you can verify. So you just take two elements of this set, arbitrary element, let's say f and t and g and t. Then you will see, you just check what is their inner product. You will see that it is 0 and therefore they are orthogonal, and their length of each of these function is also equal to 1. So it's an orthonormal set. So one means the constant function 1. Okay, so you verify this also. So now, so these are the examples of orthonormal sets. Orthonormal means orthogonal plus every vector in these sets is of length 1. So clearly you can observe here, you can make an observation here that instead of orthonormal, suppose that this set is orthogonal. This is set of vectors in an inner product space. So this is orthogonal in an inner product space, let's say V. Okay. Now can you make it orthonormal? So this set is orthogonal.
Yes, sir.
How to make it orthonormal?
Yes, sir. Norms are divide. Divide by
Divide by
Yes,
norm.
norm of itself.
yes. So these are orthogonal. So you can clearly verify that none of these vector is 0. Because if this vector is 0, then this set is not orthogonal. I mean, of course, it can be, but when we're talking about orthonormal, you cannot make it orthonormal because length is 0. It's a 0 vector. right? So by default, when you are saying this, you assume that each of these vector is a non-zero. So what you can say is that if suppose this is a non-zero, is an orthogonal set of non-zero vectors, okay, then you can make it orthonormal by dividing each vector by its norm. So just make sure that none of this vector is 0. So this is orthonormal. So any orthogonal set uh, can be transformed into an orthonormal set by dividing the vector by its norm. Okay. Now it is easy to check that every orthonormal set or orthogonal set. So whatever we are saying for orthogonal, that also applied to orthonormal set, because orthonormal set is orthogonal plus some additional property on the length. So every orthogonal set, you can verify that every orthogonal set of non-zero vectors is linearly independent. Okay, so let me write this as a result. This is very easy to verify. Every orthogonal set. So when I say orthogonal set, that means it is a set in an inner product space. Okay, or every orthogonal set of non-zero vectors in an inner product space is linearly independent. Okay, so let's see how we can prove this. So you tell me how to start. So we have to prove that every orthonormal set of non-zero vectors is an inner product space. In an inner product space is linearly independent. So how to prove this?
The
So
linear
how to start?
computation.
No, you tell me that this is how we start. So you say from the first line. So you want to prove this. So how to write this form? So we have to prove that every orthogonal set of non-zero vectors in an inner product space is linearly independent. So how to start this proof?
सर 2 केसेस बनाने पड़ेंगे, एक फाइनाइट के लिए, इनफाइनाइट।
So but why to consider two different?
बिकॉज
So
सर
let's say okay, let's say first you tell me about finite.
then so we consider some elements, मतलब some elements in orthogonal set as suppose s1 s2 s3 sn, and then take their linear combination alpha si, then put it equals to 0. Okay, and then we have to uh, uh,
Yes, I understand what you
So
want to
when we
say here. So yeah,
multiply by some vector, then all the vectors are 0 except one. So
multiply means
alpha
you
1
are
equals
saying
to
that
0 and inner
yes
multiply
sir,
means
product.
inner product.
Let's say
yes sir,
inside product.
Yeah,
Take the
yeah,
inner
yeah.
product.
Yes, I agree. So this you said that if you have a finitely many vectors, then you can do this. Now, if suppose that whatever set you have started with, suppose that it's an infinite set, and now you want to say that it is a so it's an infinite set of non-zero vectors, you orthogonal vectors. Okay, so it's an infinite orthogonal set of non-zero vectors. You want to say this is linearly independent. So how to check that? How to show that an infinite set is linearly independent?
Every finite subset is Li then.
So
Uh,
yeah, so the same trick, same argument will work there also. So you have to check for every finite combination, so you can do that, right? So you don't have to consider two different cases. Whatever you are saying for finite, just write it properly. It will also work for infinite. So for example, here you have to prove that every orthogonal set of non-zero vectors. So you start by saying that okay, let us assume let S be a subset of, let S be an orthogonal set of non-zero vectors in V. So I'm not saying it's
So,
finite or infinite. Yes.
sir, if we use John's lemma, then how to use here? क्योंकि यहाँ
Jo-
पर John's lemma use हो सकता है.
John's lemma.
Yes, sir.
In what sense? So for what you are proving this
Infinite
John's
के
lemma?
केस में sir.
No, so you just recall the definition of linearly independent set. So when we say, so let me recall here. Suppose that S is a subset of V. When we say this S is linearly independent, so if you go back to your notes, you'll see that this S is linearly independent if every finite collection of vectors in this S is linearly independent. That means if you take V1 to Vk in S, where k is natural number. So this is true for every V1 to Vk. That means any finite combination you take, and then show that this these sets are this vectors are linearly independent. So this implies alpha is 0 for all I. Then you say that this set is linearly independent. So a set is linearly independent. If it is a finite set, then you don't have to consider every linear finite combination. You just take all the vectors, take their combination, linear combination, and apply this. But if it is a infinite set, then you just check that every finite combination is linearly independent. So this is how we define. Now here you are given an infinite set. This set you have to prove linearly independent. So the same way, the only thing is that this set is also given to be orthogonal. So just to prove the linear independency, you just use the same idea. You show that every finite combination is linearly independent using the fact that these vectors are orthogonal. So you don't have to go to John's lemma here. If at all you want to use in some way. Is it okay now?
Yes, sir.
So how to do this? So you have to prove this for every orthogonal set. So you say that okay, let S be an orthogonal set of non-zero vectors. Now you have to prove that this set is linearly independent. So how would you do? So you say that okay, let V1 to Vk the same way, Vk be orthogonal in S. So any k vectors you have taken, okay? Yes. And then you say let alpha 1 V1 to alpha k Vk is 0. Right? Now this is these are vectors v1 to vk. They belong to vector space, so their linear combination is again a vector. So let's say, just for simplification, if I call this sum as u, then you can see that for each I equal to 1 to k, you can take this u inner product of u with vi. If you do this, so if you do this, then you know that each of these vectors vi, they are orthogonal. So this inner product is 0, right? But then what it is, the left hand side, the u is alpha 1 v1 to alpha k vk, vi is 0. And if you do further simplify this using the property that these vectors are orthogonal, this will give you alpha I vi inner product, let's say. Okay, sorry. So this is the left hand side. So this thing is 0 here, but then you know that vi, these vectors are non-zero. That, so therefore this implies that alpha is 0. So this implies that alpha is 0 for each I equal to 1 to k. So this implies that this set v1 to vk is linearly independent. But then this is true for any finite set of vectors in S, and therefore S is linearly independent. Okay, so every orthogonal set of non-zero vectors in an inner product space is linearly independent. Okay, So
Sir,
let
sir,
yes.
the UVI equals to 0 कैसे हुआ? यू एस में बिलोंग करेगा कि नहीं, ये तो कंफर्म नहीं है ना
You oh
सर?
so okay. So UVI 0 कैसे हुआ? Because U is 0 ना here. This here is 0, right? U is the left hand side. So UVI is 0. So you are taking the inner product of 0 with V with any vector, so it is 0. Is it okay?
Yes, sir.
Okay, so let us make this observation here. So this is fine. So the proof is over. So we make this important observation. This will be used in the next few things. So suppose that we have an inner product space. Okay, we have an inner product space, and let us assume that we have two vectors u and v in this V. And suppose that, so let me write this u. So we have two vectors. Let's say u, and we have a vector. Let's say v. Okay. So what we want to do, we want to write this vector u as a scalar multiple of v. That means let's say somewhere here, scalar multiple of v. That means some alpha v, alpha times v, plus a vector w which is orthogonal to v. So plus a vector w which is uh, something like this. So this is w. So this is alpha v. So what we want to do, so we want to write u as a, so we want to write, so let me write this. Suppose we want to write u as a scalar multiple of v plus a vector, let's say w, orthogonal to v, orthogonal to v, as suggested in this picture drawn here. So what does it mean? So that means that we want to write u as scalar multiple. So for some alpha, we want to write this u as alpha times v plus w, where w is for some alpha in the field A, and w is orthogonal to v. Okay, so this is what we want to do. So for any given two vectors u and v, suppose we want to see whether we can write this u as a scalar multiple of v plus a vector which is orthogonal to w. So if this is possible, then we know that what would be w. So from here we know that if we can do this, then w would be u minus alpha times v. So u and v are two vectors which are given to us, right? U and two vectors, we have started with these two vectors. So everything is known here if we know alpha, because if we know alpha here, if we know sorry, if we know alpha here, then we know this w, and we can write this u as alpha v plus w. So what is unknown is alpha here. So if alpha we know, then we can. But it is easy to find this alpha. So for example, if you look at how to find this alpha, so we can find this alpha by using the fact that we want this w orthogonal to v. So we want this w to be orthogonal to v. So what we can do for alpha, we know that this w and v, they are zero, they are orthogonal. So this implies that w is what? W would be of the form u minus alpha v, and then v equal to 0. But then from here, what would be alpha? Alpha would be this ratio, inner product of u with v divided by inner product of v with itself, right? So what you can say here, that yes, you can do this So if this, so from here you can write this alpha, you can find this alpha, and once you know this alpha, you can write u as alpha times v. So what is alpha here? U v divided by inner product of v with itself times v. So this is alpha v. If you look at here, this is what we are trying to do, and plus w, but w is what? W is u minus alpha v. So it is u minus alpha v. So it is this one. So what we have done here, we have written u as a scalar multiple of v. So this is alpha here, alpha times v, plus a vector which is orthogonal to v. So you can check that this w is actually orthogonal to v. So what we can say from this observation is that provided this v is non-zero, so this alpha we can always find provided this v is non-zero. That means this is possible. So denominator is not zero, then this alpha is well defined, and then we can always find this alpha for given two vectors u and v. So therefore, from this observation, we can say that if v is non-zero, if the vector v is non-zero, then its length is non-zero here, and therefore this alpha is well defined. So as long as you can find this alpha, you can always write u as a scalar multiple of v plus a vector which is orthogonal to v. So what we can conclude from this observation is that therefore thus if this v is non-zero, then this vector u can be written as a scalar multiple of v plus a vector which is orthogonal to v plus a vector orthogonal to v. Okay, so this is true for any two vectors u and v where v is non-zero. We can always do that. Now using this observation, we will first prove an inequality. It is called Cauchy-Schwarz inequality. There are several ways to prove this inequality. We will use using this observation. So let me first write this. What is Cauchy-Schwarz? Cauchy-Schwarz inequality. So what it says that let me write here. Let V be an inner product space and u and v are two vectors in V. Okay, then we have an inner product space and u and v are two vectors in V. Then the if you take the absolute of inner product of u and v, that means this one. So you take the inner product of u and v and then take its absolute value, that means the modulus. Then this value is always less than equal to product of length of u and length of v. Let us call this equation as star. Not only this, and equality holds in star if and only if u and v are linearly dependent. So for any two vectors u and v in an inner product space, this equality is true. This is called Cauchy-Schwarz inequality. And in this here, we have, instead of an inequality, we have equality. That means this left hand side is equal to right hand side if and only if u and v are linearly dependent. Okay, so the proof here, so proof follows using the observation we just made. Let me write the proof first. So first thing is clear that if v is zero, if v is zero, then what would be the left hand side? If V is 0, then left hand side is 0. Left hand side of a star
0.
is 0. And
Yes,
right
sir.
hand side?
So
What is
right
the
Also
hand
right
zero.
hand
side is 0.
is also 0. So 0 is equal to 0. So by default, this equation star is true, or it holds if V is 0. So if, let's say, V is 0, then this star holds trivially. This is clear. Okay. So therefore, without loss of generality, we can assume that V is non-zero. So because for V is 0, it is trivially holds. So we just consider the case that V is non-zero. If V is non-zero, then by previous observation, we can write U as a scalar multiple of V plus a vector W orthogonal to V. So that means then we can always write this U as alpha times V plus W, where what is this alpha? Alpha is, we know from previous observation, is this one. This is well defined because V is non-zero, and using this we can also write W, which is U minus alpha V. So we can write this U as alpha times V plus W. Okay. Now you see here this inner product. So this W is a vector. So this if I take W inner product of W with itself, then it is always, because of the non-negativity of the inner product, it is always greater than equal to 0, right? So if W is 0, then it is equal to 0. Otherwise, it is always greater than 0. So this is fine. Now you just expand this, what it is. W is U minus alpha V. You write here also U minus alpha times V. Then you open this inner product here, the right hand side. What it is, when you open this expand this inner product using the inner product property, it would be U inner product of U with itself minus alpha times V inner product of U minus U inner product of alpha times V plus inner product of alpha V with itself. Now what is this again? This is inner product of U with itself minus what it would be? The next term?
Alpha V comma U.
Yeah, inner product of V with U. Then what would be the next thing?
Alpha
Alpha
bar.
bar
Alpha bar, right?
U
Is
comma
this
V.
one, right? And similarly, if you take apply the same thing for the last term, it would be mod alpha square.
Norm. Yes.
Yeah. Okay. So now if I write what is alpha here again, what is alpha? Alpha is UV divided inner product of U with V divided by length of V square here, right? So if I will just write this, so if I write this, then what it would be the next term? So can I write this as mod of UV square divided by this one? Is it, can I write this term here as this?
Yes.
Yes. Okay. Similarly for the next term, it would be the same thing. And again, if I write for this also, it would be mod of UV square divided by length of V with itself, because it would be square, but then one term would be cancelled with this one. So this is what we have. Further, now these three terms are same. So these two will cancel out each other. So what we are left with from here, if you look at, so this is equal to, so this thing, whatever we have is greater than equal to 0, but then this, whatever we have is equal to this. So the whatever we have at the end, we can write from here is that 0 is less than equal to inner product of U with itself minus this one. Okay, let us call this equation, let's say some double star. Now from here, what you can say from this equation, you can say that if you take this term with a negative sign to other side, what it would be? It would be this one, right? But then you can take this term also to other side because v is non-zero. So you can this term you can take you can take to other side. So what it would be? You can write it in this way, right? So let me write it clearly. This is what we have. But then what is right hand side? Right hand side here, this term is equal to length of u square. This term is equal to length of v square. You take the square root both sides. So what you will get is that inequality, right? So this proves the star. So you have proved star. So you can see that we have not assumed anything. Just use the fact that v is non-zero. If v is non-zero, then we can do this and we can prove the inequality. So this proves half of the result. That means up to this we have proved. Now we have to prove that equality holds in star if and only if u and v are linearly dependent. Now one thing is clear, that this inequality here in double star, this is coming from here. So if you look at this one, how did we get this? We get it from here. So the whatever is this is the right hand side, this one actually. Okay. Now when we have strict inequality here, then we have strict inequality here in this, because it's coming from there only, right? So when is this inequality strict here? So when do we have strict inequality in this?
W non-zero.
When W non-zero. So when W is non-zero, this implies what? So from here you can clearly say that from one, or from double star, sorry, from double star, you can say that if W is not equal to 0, then this inequality is strict, right? And therefore, this equality holds if and only if W is 0, because W is non-zero, then it is strictly unequal. Strict inequality holds. So equality holds if and only if W is 0. But when W is 0, now look at this. What happens when W is 0? So W is 0 if and only if. So
U
you
minus
look at
U equals to alpha v.
U minus alpha v equals to 0.
right. So W is 0
Yeah.
if and only if, yeah, if and only if U is equal to alpha v. But that means what? That means U and V are
Linearly
linearly
dependent.
dependent, and we are done. So now you see that because of that observation, the proof is very immediate. You can also, so I'll just state this some of the properties of for the length of a vector in an inner product space. You can verify them easily using whatever knowledge we have so far. Just simple calculation is there, one line calculation. So I won't do this and I will save some time here. So let me write this as a result. Suppose that we have an inner product space V over F. Then you can easily verify that the first thing, that if you take length of any vector alpha V, alpha times V, where alpha is a scalar and V is a vector in V, then this length is equal to, can you guess what it could be?
mod alpha norm B.
Mod alpha length of V. Yes. So this you can verify for any alpha and B. Okay. Similarly, if you can easily verify, this follows just by definition. The first inequality, the first item here follows because of the definition of vector space or definition of an inner product. Similarly, you can see that for any vector V, length is always greater than 0 if V is non-zero. This also you can easily check by definition of inner product, the first property of inner product it is actually. Similarly, you can verify that if you take any two vectors, then the length of the sum is less than equal to sum of their length. So this is true for all vectors u and v in the inner product space V, and it is called triangle inequality.
Triangle inequality.
Yes. So this also you can prove this triangle inequality actually you can prove using the Cauchy-Schwarz inequality. How would you prove this? So let me give you some hint here to prove this third one. So the first two items here, they follow by definition. Uh, for the third one, you can use Cauchy-Schwarz. So the hint is that you use Cauchy-Schwarz. So what you have to do here, you just take the left hand side like this one. So the left hand side is what? By definition, it is u plus v inner product with itself. Then you just expand this using the inner product property, and at some point you have to use Cauchy-Schwarz. Okay, and then you can easily do it. Okay, so this is the hint for this third one. The fourth one is it says that if you take any two vectors u and v which are orthogonal to each other, such that u and v are orthogonal, then you can show that the length of the sum, the length of the square of the sum of the these two vector u and v is equal to sum of their uh, square of their length. So it's equal to u square plus length of v square. So
Right angle property.
this is called Pythagorean theorem. So if you recall from Pythagoras Pythagoras theorem, it is the same thing. So it is known as Pythagorean theorem, right? And then we have one more property. If you take any two vectors u and v, then you can show that if you take if you look at this one, you take the square of the length of u plus v plus square of the length of u minus v, then it is equal to twice of sum of square of their lengths. And this is now, if you just recall this, then this is called the parallelogram law. Parallel. Yeah. So this is called parallelogram law. Okay. So these are simply you can prove this with just using the fact whatever is given to you. For example, here the first two you just use the definition. Third one, as I have mentioned, you just use the Cauchy-Schwarz. Similarly, in the fourth one, just use the fact that u and v are orthogonal, and you can easily, so you start from here, then you just keep on simplifying it using the fact that u and v are orthogonal. You will get this one. Similarly, here also you just start by expanding the left hand side, and then you will get that this is equal to the right hand side. All right, so this is uh, this is regarding the length of a vector in an inner product space. Now you have seen, so let me, before I state the next thing, let me ask you this. Suppose that we are in R2. Okay, so this is done here. Okay, you can complete the proof. So now I want to make a statement here, but before that, let us consider this inner product as V as, let's say, R2. Okay, now clearly in R2 with a standard inner product. Okay, with a standard inner product. So in R2, clearly, if you look at this uh, x-axis and y-axis, then they are perpendicular or orthogonal to each other. Okay, so any vector if you take here, let's say in particular 1 0 or 0 1, if you take, then clearly these vectors are orthogonal. We have also seen this, so you can see it simply. But for this inner product, if I take let's say let us call this vector as e1, this is e2, and let's say some vector, let's say x1, then clearly this x1 is also a vector in R2, and if I take e1 x1 or let's say e2 x2, then this set, so, and let's say e1 e2, then clearly this is orthogonal, in fact orthonormal, but this set is not orthogonal, this is also not orthogonal. But you can check that this forms a basis. That means this is, if you take the span of the first one, it will give you R2. Similarly, these two vectors are also linearly independent. So let's say this vector is 1 1. Okay, so these are also linearly independent. They also form a basis for R2. So what you can say from here that every, what we have proved here is that every non-zero set of vectors, orthogonal vectors, is linearly independent. This is what we proved, right? If you look at here, what we proved that every orthogonal set of non-zero vectors in an inner product space is linearly independent. But the question is whether the converse is true. Can we say that every linearly independent set of vectors in an inner product space is orthogonal? So what is your answer?
No, sir.
No, and we
No,
have
sir.
already seen, yeah. So you can see here what I mentioned here, that they are linearly independent, but they are not orthogonal.
Orthogonal.
But then the question is, okay, if they are not orthogonal, can we make them orthogonal? Or if the set is not orthogonal, it is linearly independent, but it is not orthogonal, can we make this set orthogonal some way? And the answer is yes, you can do that. The set itself may not be orthogonal, but using these given linearly independent vectors, you can generate a new set. That new set is orthonormal, not only orthogonal, but it spans exactly the same set which is spanned by the given linearly independent vectors. So what I'm saying is that, okay, here this e1 x1 here, this set is linearly independent, but it is not orthogonal. But using this, you can form a new set, let's say v1 v2, such that this v1 v2 is orthogonal. You have to generate this orthogonal, or we can generate this orthogonal set v1 v2 using the given e1 and e1 and x1 here, such that span of e1 x1 is same as span of v1 v2. So we can say that this set is not orthogonal, but we can use this set to find an orthogonal set that spans exactly the same set which is spanned by e1 and x1. Not only for R2, but in general for a vector space, for an inner product space, we can do that. So if we have an inner product space and we are given a set of vectors, let's say linearly independent set of vectors, then using these vectors, we can construct an orthogonal set. We can also generate similarly an orthonormal set, such that uh, the new set spans exactly the same set which is spanned by the given set of vectors. Okay.
Yes, sir.
Okay, so let me erase this one. This result, this I will write and I will explain this process how to do that as a, by when while proving this result. So I will first state this result. This result is a well-known result. It is called Gram-Smith orthogonalization process, and I will explain this process while proving this. Okay, so how and the proof of this result will also give you a way how to generate orthonormal or orthogonal set depending what you want from a given linearly independent set of vectors. All right, so let us first state this result, understand the statement first, and then look at the proof. So let me write this so I can write it on this new page. So it is called Gram-Smith orthogonalization process. So what it says, so I will write this as a result here. So suppose that we have an inner product space V, and in this inner product space we have a finite set of vectors which is linearly independent. Okay, so we have a linearly independent set of vectors in V. Then, so let this set be linearly independent. Then one can always construct an orthonormal set. You can, I'll do it for orthonormal, but you can always generate an orthogonal set also. So then one may construct and so let us do it for orthogonal. Okay, so orthogonal set, let's say Q1, Q2 to Qn, subset of V. So using these vectors V1 to Vn, one may construct an orthogonal set Q1 to Q1 in V such that the span of V1 to Vk is equal to span of Q1 to Qk for each k equal to 1 to n. Okay, so what it says that if we are given a linearly independent set of vectors, let's say v1 to vn, the finite linearly independent set of vectors in V, then using these vectors we can construct an orthogonal set of vectors q1 to qn such that span of v1 to vk is equal to span of q1 to qk for all k equal to 1 to n. That means when k is equal to 1, so this result says that span of v1 is equal to span of q1. Similarly, if you look at span of v1 to v1 and v2, it is equal to span of q1 and q2, and so on up to all v1 to vn. It is equal to span of q1 to qn. This is what it's saying. It is saying. Okay. So how to prove this? Uh, the proof we will understand. First, we will first understand the first two. First, we will first generate 2-3 vectors so that we understand the process, and then we can use the induction to prove this. Okay, but let us first understand how to do that. So let me explain this. So suppose that we have, instead of this n vectors, let us assume that we have only one vector v1. It's linearly independent. Okay, so suppose that we have only one vector v1. So v1 is linearly independent means v1 is a non-zero vector. It's just one vector. Then how can we generate a orthogonal set q1 such that the span of v1 is equal to span of q1? Can you tell me what would be that q1?
Sir, V1 itself.
V1 itself. So when we have just one vector, then we can take Q1 as V1. So it's a non-zero vector. So it is orthogonal to itself by definition because there is no other vector. So and also span of V1 is equal to span of Q1. So clearly you can say that span of V1 is equal to span of Q1. Or let me write this way, this side. So you take Q1 as V1, then clearly span of V1 is equal to, so clearly span of V1 is equal to span of Q1. So when there is only one vector, there is nothing to do. It's very straightforward. Now suppose that we have two vectors. So suppose we have V1. So from V1 we have already generated Q1. Now suppose that we have V2 also. So V1, V2. So we need to generate now the second vector Q2 here, such that Q1, Q2 are orthogonal and span of V1, V2 is same as span of Q1, Q2 because span of V1 is already, we have proved span of V1 is already span of Q1, right? So we have to generate this Q1 here that we don't know yet. So this we can do if you just recall what we did in the previous observation. So what we did here. So recall that what we have, we have V2, V1. So from V1 we can generate Q1. So that is easy. But then we need to generate Q2, right? So but what we have Q1 and V2. These two things we have, right? So we have Q1 and V2. These two vectors we have. Now we know that we can write this V2 as a scalar multiple of V1 or Q1 plus a vector which is orthogonal to Q1. This vector I can call as Q2 because my aim is to find a vector Q2 which is orthogonal to Q1 and it spans the same space. So you will see that, so clearly I can do this because Q1 is non-zero. Because V1 is non-zero, so Q1 is non-zero. So I can always write V2 as a scalar multiple of Q1 plus a vector which is orthogonal to Q1. So Q2 is clearly orthogonal to Q1 and I know how to find this, right? So what would be Q2 my? So this Q2 would be V2 minus alpha Q1, but I know what is this alpha, right? So alpha would be V2 Q1 divided by length of Q1 square. This is from this observation. So clearly this we can do. So this way we can find Q2. So we get a vector Q2, but can you check what is the span of Q1 and Q2? Is it same as the span of V1 and V2? So
Yes, sir,
what
it is same.
it is same? Why it is same? Because Q1 is just V1. So
Yes,
here
sir.
you can see that Q2 is actually V2 minus some scalar multiple of Q1, but Q1 is actually V1.
Yes,
So Q2 belong to V1, V2. Q1 also
yes,
belong to V1, V2. So span of Q1, Q2 belong to span of V1, V2. And similarly, you can check the other side also. Span of V1, V2 belong to span of Q1, Q2. So clearly, you can say that if we have two vectors V1 and V2, then we can find Q1 and Q2. Q1 is just as V1 and Q2 would be. So now you can find this second vector Q2. So what you do, you find this Q2. Sorry. So the second vector, let me write this Q2. So second vector Q2 I can choose as V2 minus V2 Q1 because Q1 I already know. So I can use this Q1 and I can construct this second vector Q2, right? Now clearly up to two vectors I am done. So this Q1, Q2 are orthogonal and span of V1 is equal to span of Q1 and span of V1, V2 is equal to span of Q1, Q2. This is fine. Now suppose we want to generate the third vector. So now suppose we have V1, V2, V3 out of this, from this v1, v2, v3, we already have q1, q2. We have to generate the third vector q3. Now, in order to generate this third vector q3, we will use the same idea which we use to find q2. So what I'm saying is the following, that you use exactly the same idea. So let me first write the second step here. So clearly from here, this q2 is orthogonal to q1, and also span of q1, q2 is equal to span of v1, v2. Okay. Now we want to generate the third vector. So what I'm saying is that there is nothing special about two vectors. The same idea can be generalized for three vectors also. So what I'm saying is that you generalize the same idea which you use to find q2. So what we have now, we have q1, we have q2, and we are given v3 also. So what I will do exactly the same thing. I want to write this v3 as a scalar multiple of q1 plus some scalar multiple of q2 plus a vector q3 which is orthogonal to q1 and also orthogonal to q2. Okay, so what I'm saying, I'm asking the same question which I asked to find q2. Can I do that? You can see that whatever observation we made here, in order to show that two vectors, for every two vectors u and v, as long as v is non-zero, we can write u as a scalar multiple of v plus a vector w which is orthogonal to v. But instead of two vectors, if we ask the same question for three vectors, then you can see you can apply exactly the same process, and you can show that as long as the two vectors are non-zero, that means in this context, if q1 and q2 are non-zero, then you can find the third vector q3 such that this q3, this v3 is a scalar multiple of is equal to alpha times q1 plus beta times q2 plus q3, where q3 is orthogonal to q1 and also orthogonal to q2. Now, how this is possible? This you can do the same way. You can find alpha by using the fact that q3 and q1 are orthogonal and q1, q2 are also orthogonal to each other. And then you can find beta using the second property. So what I'm saying is that you can use the fact that you want q2 orthogonal to q1, q3 orthogonal to q2. So using this, you can find alpha. So alpha would be, can you tell me what would be alpha here? Can you find value of alpha here?
v3 comma q1 by q1 into q1.
Yeah, scalar multiple of q1 with itself. Similarly, you can find beta also. It will be v3, sorry. It would be v3 q2, yeah, divided by q2 length of q2 square. So if you know alpha and beta, then clearly you can write this q3 is v3 minus alpha q1 minus beta q2. So where alpha and beta are defined as this. This q3, clearly the way you have constructed, this q3 is orthogonal to q1 and q2 both. So clearly q1, q2, q3, they form an orthogonal set because q1 and q2 are already orthogonal, and now you have constructed the third vector which is orthogonal to both q1 and q2. So this q1, q2, q3, they form an orthogonal set. And not only that, now again you check what would be the span of v1, v2, v3. Is it equal to span of q1, q2, q3?
Yes, sir.
Yes, is using the same fact. Because why this is? because you see here this Q3 belong to span of V1, V2, V3 because here Q1 is just a span of V1, Q2 belongs to
Yes,
span
sir.
of V1 and V2.
One
So
with
this,
two.
yeah, this belong to span of V1, V2, V3. So that means Q3 belong to span of V1, V2, V3. We have already shown that span of Q1, Q2 is equal to span of V1, V2. So Q1, Q2, Q3 both belong, all three belong to span of V1, V2, V3. So their span also is a subset of span of V1, V2, V3. But then the other side is also true. Same way, you can show that span of V1, V2, V3 belongs to span of Q1, Q2, Q3. So what I'm saying is that using this idea, you can find the third vector also. That what I'm saying, you set the third vector, set Q3 as Q3 as V3 minus this one V3 comma Q1 divided by length of Q1 square minus V3 comma Q2 divided by length of Q2 square. Oh, sorry, here it is Q1 and then. So it is here it is Q1 minus V3 Q2 divided by length of Q2 square, then this is Q2. So clearly from here you can say the way you have constructed this Q3 is orthogonal to Q1 and Q3 is also orthogonal to Q2. So basically Q1, Q2, Q3 they form an orthogonal set, and also you can check that the span of V1, V2, V3 is equal to span of Q1, Q2, Q3. So we have generated three vectors Q1, Q2, Q3. But again, there is nothing special about these three vectors. The same idea you can use for four vectors also. So in fact, for any given set of vectors, you can use the same idea and you can construct the next vector. Using this idea, keeping this in mind, we can use the induction and we can prove the statement by induction. So let me just write this and then you can verify the details here. So I have 2 minutes, so I want to finish this. And then in the next class, we will see some examples. So is the idea clear? Up to this, can you, so if I give you three vectors, can you construct the three orthogonal vectors? So
Yes,
if
sir.
I give you V1, V2, V3, right? So the same idea you can use to generate the fourth vector, the next vector, that means Q4. The same way, instead of now asking this question for three vectors, you can ask this for Q1, Q2, Q3 and V4. Use the same idea and you will get this. So in fact, you can prove it for any given set of vectors, finite set of vectors. So what I'm saying is that you can prove it by induction. So what does it mean? It means that, so you can use this induction this way. So I'm just writing this. You can verify the details. If you have any doubt, I can explain in the next class so that I don't have to repeat the same thing in the next class. So suppose for uh, m less than n, an orthogonal set, let's say Q1 to Qm has been constructed. Such that span of V1 to Vk is equal to span of Q1 to Qk for each k belongs to this. Okay, now to construct the next vector, so can you tell me now what would be the next vector just by using this idea? Just tell me what would be Qm plus 1 to construct the next vector. Let, so what would be the next vector? Let's say Qm plus 1. Can you tell me what it would be? Just give me
Vm plus 1 minus
Vm plus 1 minus,
summation
Vm plus
yeah, summation, you can write j equal to 1 to m Vm plus 1 Qj divided by length of Qj square Qj. Okay. Now this vector I got using the same idea. I apply the same idea on the given m orthogonal vectors, and using these orthogonal vectors I use the next vector. I found the next vector. Now you can verify that this next vector is non-zero, so you can verify all the details. That then if you construct this qm plus 1 this way, then you can verify that this vector qm plus 1 is non-zero. Why this is non-zero you can verify, or maybe I'll ask this question in the next class. Not only this next vector qm plus 1, this is orthogonal to all the qj's where j is from 1 to m. So this is 0 for j equal to 1 to m. So that means this set q1 to qm plus 1, this is orthogonal. And not only this, the span of q1 to qm plus 1 is equal to span of v1 to vm plus 1. So with these three observations, you are done. Okay. So you verify these three things: why the first one is true, why the second one, and why the third one. These are very straightforward thing again, but you verify yourself. If you have any doubt, I can explain this in the next class. So we can stop here, and as usual, we will have a tutorial class from 2 to 3 in the afternoon. So we can stop here.
सर
Yes.
सर मैंने ग्रेड स्कोप पर रीग्रेड की रिक्वेस्ट डाली थी, वो अभी भी पेंडिंग है.
Abhi pending. Yes, I agree, because I was not here. I went for this JE exam duty, so I was not here the last 3 days. So I will check this. So don't worry, you have already put up the request, so it is on my desk. So whenever I get time, I will check the papers again.
ओके सर.
Okay, I'll let you know. I'll send an email saying that or you can also check on the grade score that it is resolved. But I won't be able to do it today. Maybe tomorrow or day after tomorrow. I'll get some time. So,
ओके.
okay.
सर
Anything else? Yes.
सर सर लास्ट वर्किंग डे हम जो क्लास थे ना, उसमें एक ऑब्जर्वेशन आपने चेंज करवा दिया था कि जो ए बी है वो ग्रेटर देन 0 लेना पड़ेगा. वो एग्जांपल
हाँ.
था v इक्वल्स टू सी ए बी. तो उसमें वो कोई मतलब ए बी को कोई जरूरी नहीं कि आप ग्रेटर देन 0 लो. मतलब मैंने वेरीफाई करा था उसको.
Yes. So
तो
actually, the way we have written just the lower limit and upper limit in the integration. For that we consider it that okay. Let us assume that it is in the in only one half.
या सर.
Okay.
बट एक्चुअली मैंने जैसे वो एग्जांपल बताया था x वाला -1 to 1, तो वो मैं गलत था उस समय. वो x 3/3 हो जाएगा, देन आफ्टर वो 2/3 आंसर आएगा उसका. उस समय मैं
Yeah. So
गलत
it's
कैलकुलेशन कर रहा था.
okay. So you just verify this. Whatever is wrong, it's good if you have realized that, then there is no issue. Okay, good.
सर
थैंक यू सर.
Yes.
सर
Yes.
सर आरएन में आपने बोला था जो बेसिस होता है और डुअल बेसिस दोनों सेम होता है. सर ये समझ में नहीं आया.
This you can you just use the fact that what we want set of vectors that satisfy this property. Um, that what was that? Fi vj is equal to del ij. So using that, so it's basically for Rn. In Rn, yes, I agree. I understand what you mean by that. So in Rn, especially in Fn, this set v dash is identified as v itself. Because why this is? Because there is a isomorphism from v to v dash also. So maybe I'll explain this in the next class, why you can consider these under certain isomorphism. You can treat the vector elements of v dash as elements of v itself under certain isomorphism. Okay.
Thank you, sir. Have a good day.
Okay,
Thank you,
same to
sir.
you. Yes. So we can stop here. I'll see you in the next class. Bye.
Thank you, sir.
Yeah.
Hello, sir.
Hello. Yes.
Can you hear me, sir?
Yes.
Sir, I have doubt in lecture